Hello dear students, welcome to mathematics class. In this class, let us start with the second unit of paper 1. So, here it is the second unit, Riemann integration. So, it is the continuation part of the first unit. So, the syllabus of this unit is integrity of continuous function, monotonic functions, fundamental theorem of integral calculus, change of variables, integration by parts, and the first and second mean value theorem. So, there first mean value theorem is called as Bonnet form of the theorem, and the second one is Weierstrass form of the theorem of integral calculus. So, it is the content in the second unit. Now, let us start with the first theorem of this unit. So, here it is the statement of the first theorem. The statement is every continuous function is R integrable. Every continuous function is R integrable or Riemann integrable function. So, let us prove this one. Let f be a continuous function. Let f be a continuous function on a closed interval a b. So, therefore, here it is the continuous function f. Let p is equal to a equal to x naught, x1, x2, so on up to xn equal to b, be a partition of closed interval a b with norm of p less than delta. Norm means that is the maximum length of the subintervals. So, each subinterval must have the length which is less than delta. Let capital MR and small mr be supremum and infimum of f on the rth subinterval which is denoted as IR. Now, consider, to prove that f is Riemann integrable, here we are going to use the necessary and sufficient condition, that is UPF minus LPF is less than epsilon. So, therefore, now consider UPF minus LPF is equal to. So, by using the formula for the upper Riemann sum, so it is equal to summation over R is equal to 1 to n capital MR into delta R minus summation over R is equal to 1 to n small mr into delta R. So, by using the definitions of upper and lower Riemann sums, here we have upper Riemann sum is equal to summation over R is equal to 1 to n mr into delta R. Here capital MR is the supremum of the function f on the rth subinterval, and this summation over R is equal to 1 to n small mr delta R. So, it is the infimum of the function f on the closed interval IR, that rth subinterval. So, it is equal to summation over R is equal to 1 to n capital MR minus small mr into delta R by taking the common. That summation is common because in both the expressions R is varying from 1 to n and delta R is also common. So, therefore, it is summation over R is equal to 1 to n capital MR minus small mr delta R. Now, it is equal to summation over R is equal to 1 to n, this mr minus mr, that is the supremum of mod of f of x minus f of y. into delta r, where x and y are the elements of rth sub interval. So, here f of x, f of y. So, already we know that if f is bounded on the closed interval a b with the bounds capital M and small m, then m minus m is equal to supremum of the set mod f of x minus f of y, where x comma y belongs to the closed interval a b. So, therefore, by using this condition we have written that mr minus mr. So, these are the bounds of the function f in the rth subinterval IR. So, here mr is the supremum and small mr is the infimum. So, similarly here capital M is the supremum and small m is the infimum. So, therefore, this oscillation means the difference between upper and lower bounds. So, therefore, this oscillation is nothing but it is the supremum of mod f of x minus f of y. Now, UPF minus LPF is equal to, so here this supremum of mod f of x minus f of y as it is. Now, apply the summation for delta r, that is summation over r is equal to 1 to n delta r. Now, this is equal to supremum of mod f of x minus f of y into b minus a, because the sum of lengths of the all the sub intervals is equal to length of the main interval, that is the length of the interval a b. So, therefore, this sum is equal to b minus a. Next, as the function f is continuous on a closed interval a b, hence it is uniformly continuous. If f is continuous on a closed interval, then we can say that it is uniformly continuous on the same interval a b. Then, by definition of uniform continuity, for any epsilon greater than 0, there exists delta greater than 0 such that for all mod f of x minus f of y less than epsilon, it implies that mod x minus y less than delta. Now, here, so it is the definition of uniform continuity. For any epsilon greater than 0, there exists delta greater than 0 such that if f of x minus f of y is less than delta, then x minus y is less than, f of x minus f of y is less than epsilon, then mod x minus y less than delta. Since epsilon is arbitrary, so therefore, choose epsilon is equal to epsilon divided by b minus a. So, therefore, mod f of x minus f of y, this is less than epsilon divided by b minus a. Consider this as the second equation, because epsilon is arbitrary constant, then it can take any value. So, therefore, for our convenience we have considered that as the epsilon by b minus a. Now from equations 1 and 2, from equations 1 and 2, the equation 1 is UPF minus LPF is equal to supremum of mod f of x minus f of y into b minus a, right. And here we got the value for mod f of x minus f of y, and it is, this is the supremum. Supremum means that is the upper bound. So therefore this value must be, or this f of x minus f of y is less than epsilon divided by b minus a into b minus a. So therefore this, here we are considering supremum of mod f of x minus f of y. Since f of x minus f of y is less than epsilon divided by b minus a, and its supremum is also less than epsilon divided by b minus a into b minus a. Here b minus a get cancelled, remaining epsilon. So therefore UPF minus LPF is less than epsilon. It implies that f belongs to R of closed interval AB. Means here UPF minus LPF is less than epsilon, means by using the necessary and sufficient condition for Riemann integrability, we can say that f is R integrable over the interval AB. So therefore it is the required proof. Here we have proved that every continuous function is Riemann integrable function. If the function is continuous in a specific interval or any bounded interval, then we can say that in the same interval the function is Riemann integrable. The next theorem is every monotonic function is R integrable. So here monotonic means it may be increasing or decreasing. So therefore here proof, let the function f be monotonic in closed interval AB. Monotonic means if the function is increasing throughout the domain AB or throughout the closed interval AB, and it should not decrease in between. So therefore that is called as monotonically increasing function. And similarly if the function is decreasing throughout the domain, then we can say that it is monotonically decreasing function. Now assume that f is monotonically increasing. Let us assume that f is monotonically increasing. Let p is equal to a equal to x naught, x1, x2 and so on up to xn equal to b be any partition of the closed interval AB. So here we are assuming that f is monotonically increasing, means f of x n is always greater than or equal to f of x n minus 1, means the value of the function f at x n must be greater than its previous value, that is f of x n minus 1. So that is the increasing function. So here we are considering the partition P of the closed interval AB such that norm of P is less than delta. Now capital MR and small mr be the supremum and infimum of f on the rth subinterval IR, such that f of xr must be equal to mr, means the supremum is equal to f of xr and f of xr minus 1 equal to small mr. So, here IR is equal to what? XR to XR minus 1, that is the rth subinterval, sorry, XR minus 1 to XR. XR minus 1 is the lower bound of the interval and XR is the upper bound of the interval. So, therefore, for upper bound the value of the function must be equal to supremum of the function, and for lower bound XR minus 1 the value of the function is equal to infimum of f. Now, consider UPF minus LPF is equal to summation over r is equal to 1 to n capital MR into delta r, and summation over r is equal to 1 to n small mr into delta r. So, by using the formula for the upper and Riemann sums. So, upper Riemann sum equal to summation over r equal to 1 to n supremum into delta r, and here it is infimum into delta r. Now, by taking the common terms, that is summation over r is equal to 1 to n capital MR minus small mr into delta r, and this is equal to, so here delta r is common and similarly summation is also common, and this is equal to f of xr minus f of xr minus 1 into delta r, because capital MR equal to f of xr and small mr equal to f of xr minus 1. Now, let us expand this one by substituting the value for r. Now, this is f of x1 minus f of x0 plus, for r equal to 1 this becomes x1 and this is 1 minus 1, that is 0, and for r equal to 2 this is f of x2 minus f of x1 plus, for r equal to 3 it is f of x3 minus f of x2, and so on. For r is equal to n, this becomes f of xn minus f of xn minus 1 into, let us consider this as summation over r equal to 1 to n delta r, right. We are not applying this, consider this whole as the summation, that is summation over r equal to 1 to n delta r, and only expanding the first expression, that is f of xr minus f of xr minus 1. Now, it is equal to, here f of x1 is positive and in the next one that is negative, right. So, therefore, these two will get cancelled, and similarly f of x2 in the second term is positive and it is in the third term will be negative. So, therefore, f of x2 will get cancelled, and similarly here f of x3 is positive, then in the next expression that will be negative. So, like that all the terms will get cancelled, only remaining is the first, that is minus f of x0, and here it is f of xn, because we are not considering the next term of this one. If you consider r is equal to n plus 1, then this n becomes n minus this f of xn becomes minus f of xn in the next interval, and this f of xn minus 1 will be positive in the previous term of this expression. So, therefore, here this will also get cancelled with the previous term, then all this will become f of xn minus f of x0 into summation over r is equal to 1 to n delta r, and f of xn. So, here f of xn can be written as f of b, because in the partition xn equal to b and x0 equal to a. So, therefore, x0 can be written as f of a and f of xn can be written as f of b, and this is less than f of b minus f of a into delta. So, here we know that norm of P is less than delta, means length of each sub interval must be less than delta. Then the total sum of them, the total sum of each sub interval must be less than delta. So, therefore, this total expression becomes less than f of b minus f of a delta, and on LHS we have UPF minus LPF. So, here delta is length of any sub interval. Now choose delta is equal to epsilon divided by f of b minus f of a plus 1. So, here in the equation we have UPF minus LPF is less than f of b minus f of a into delta is there, right? It is the equation. Now, we need to prove that this difference upper sum minus lower sum is less than epsilon, then only the function becomes R integrable. So, that we are choosing the value for delta. So, the delta is independent, means that is the length of interval that we can choose as our convenience. So, therefore, this total must be less than epsilon. So, that is why we are considering epsilon divided by f of b minus f of a plus 1, because here it is f of b minus f of a. If we consider that epsilon divided by f of b minus f of a, then that becomes f of a and f of b will get cancelled, and that is equal to epsilon. That should be less than epsilon. So, that is why we are increasing the denominator by 1. So, therefore, here f of b minus f of a into epsilon divided by, so here it is less than or equal to, and this is f of b minus f of a plus 1. Now, this f of b divided by f of b minus f of a plus epsilon, that is always less than 1, because the denominator is greater than the numerator, then the ratio must be equal to less than 1. Hence, the number which is less than 1 into epsilon, that becomes strictly less than epsilon, right. So, therefore, UPF minus LPF is strictly less than epsilon. Hence, by using the necessary and sufficient condition, we can say that f belongs to R of closed interval AB. So, here we have proved that every monotonic function is Riemann integrable by using the necessary and sufficient condition for R integrability.